Okay, so welcome to lecture 10, I think, in Dynamical Systems. So what I'm going to do today is go on and look at techniques beyond linearization. Linearization we've done so far, it works in 1 and in 2 dimensions. And as we saw in this example, simply by plotting the eigendirections at the fixed points, where you've linearized about every single fixed point, gives you a really good idea of what the phase portrait looks like. And the rest you can draw in by hand, or you can in fact draw them in with a computer, like we discussed in the tutorial. And if you did not attend the tutorial and you don't know how to work with Python, please at least listen. I'll upload the lecture, listen to what was discussed there. If you do know how to work with Python, go to the example that's on the website and download it and run it so that you can change the functions and have a means of plotting or exploring other dynamical systems as well. Because all you have to do basically is change this function right at the top over here and then change the plotting thing that plots the null lines, and you can actually go and produce exactly what I did on the slides. Okay, so I encourage you to do that. I encourage you to play with it because it gives you an intuitive feel of what the stuff looks like, and it makes it a lot easier when you actually are working out the phase portraits, if you've played with some of these, to just know what to draw. Okay, but now the topic for today is going to be, does this always work? So does linearization about the point always give us a definitive answer? And we can see we already have an inkling that there is trouble, because remember when we did the one-dimensional case, the moment we had a fixed point and the derivative vanished, we knew we were at a bifurcation point, but we could also not classify whether the fixed point was stable or not. If the derivative vanished, remember the fixed point could be either semi-stable, where you approached it from the 1 point, paused there, but if you pushed it a little bit it would run away to infinity. Or it could be stable if you had this cubic thing that had with a negative cubic sign, or it could be unstable if you had a different cubic. So there were many possibilities. And the same thing is actually true in 2 dimensions, and I'm just going to illustrate this. But the thing in 2 dimensions, if linearization fails, you have a number of other things that can go wrong as well. So we just want to enlarge what we know to the 2-dimensional case. And so the question is basically, does linearization give qualitatively correct dynamics near X star? And the answer is yes, provided your eigenvalues are not 0. Okay, so that basically means if you think back, so that's a more succinct statement than what I'm actually going to give you, but if you think back to that plot with a parabola where I put the various phase diagrams on the parabola, and where you had the saddle and the fixed points and the stable ones, linearization works everywhere except on the lines that we drew. Okay. And so the exact statement is linearization works if we have a saddle, in other words, if the determinant is negative, if we have a node, in other words, where the determinant is positive and the traced is either positive or negative, or a spiral, in other words, the determinant is positive, the trace is positive or negative, and we have complex eigenvalues. So those things are robust. So if you get a linear result and you get one of those, then you know you can stop there, you don't have to go further, you know what the thing looks like past the fixed point. The places where it doesn't work, and I'm going to actually give you an example that illustrates that, the borderline cases. In other words, all those cases, as I said, that are lines on their diagram, the phase diagram, that's possible for various traces and determinants. All those borderline cases, such as degenerate nodes, the star, the center, and isolated fixed points. That's basically being on the line where delta is 0, like that delta equals to 0 line. All those cases can be altered. In other words, by the higher order terms. So when you have one of those cases, like on the lines in that diagram, then you must know, you must look at the full nonlinear equations, and you must make a different plan. They may be what they say they are, but they may also not be. And so the example that I'm going to show you is simply to illustrate this. Okay. So let's have a look at this example. Right? Simple one. It's cubic in x and y. It's got this linear term. So, and cubic in x and y over there. So we want to analyze the system and see what it does. And when we analyze it, we basically want to classify the fixed point. And we can see from here, there's a fixed point if x is equals to 0, 0. It may not be the only fixed point, but it definitely is a fixed point. And so the question is, if we look at this fixed point and we linearize the problem about this fixed point, what do we say about it? So let's work out the Jacobian. We work out df dx over there, and it is simply 3ax squared plus ay squared. Df dy is this, so the y comes in there. Dg dx is there. Dg dy is over there. So that's our Jacobian. And if we now evaluate the Jacobian at 0, 0, we get this thing. Okay, so we have 0 eigenvalues. So we are on, and our trace is 0, so we're on basically the trace. We don't have 0 eigenvalues. We have complex eigenvalues, but we have 0 trace. So we are sitting on this vertical axis on that plot I made. And furthermore, the determinant is 1, so it's positive, the trace is 0, and so we have a center. Okay. So that's what linearization predicts. And so we can go back here and say, oh, but it's a borderline case. It sits on one of those lines in my classification. Is this really true? And we know we must go and look at the equations more carefully. And so the analysis for looking at these equations more carefully that I'm introduced is going to be a technique that you're going to see in other cases as well, which is why I give it to you. So what we're going to do is we're going to try and analyze the full nonlinear system, and here we can actually do it. And the way we analyze it, we change coordinates. And this becomes an art form. When you're dealing with dynamical systems, you capture the same, you're describing the same system, it doesn't matter what coordinates you're in. But if you choose the right coordinates, often the problem is a lot easier to analyze than if you're just in the random wrong coordinates. And choosing the right coordinates, there are some systematic ways of doing it. Whenever I see them, I'll tell you, but most of the time it's experience. That you know certain structures appear in the coordinate system and that there are better coordinates for them to work in. So for example, my experience tells me if I look at this dynamical system, I've basically got this quantity x squared plus y squared and x squared plus y squared, and I have their derivatives sitting over there. And so my guess at the best coordinates to choose would be a coordinate where this x squared plus y squared becomes our new coordinate, okay, or a function of it. And this is actually the same as polar coordinates. So if you were to transform so rather than just give you what it is, I'm telling you why I would have guessed that. Okay. So if I introduce new coordinates and I say y is equals to r sine theta and x equals to r cos theta, so my new coordinates are basically r and theta, what I have then is that the new coordinate r squared is basically x squared plus y squared. And then you always need an additional independent one, and we have tan theta equals to y over x. Okay, so my reason for guessing polar coordinates is because I saw this x squared plus y squared term. If in both equations I'd seen an x squared plus, say, 4y squared term, I would have chosen elliptic coordinates. Okay, I would have chosen something that would basically have had a 2 over there, so that when I work this thing out, I have the x squared plus 4y squared coming in. Okay. So that's my choice of coordinates. what I'm now going to do is I'm going to write this ordinary differential equation in terms of the new coordinates. And this is a technique I want you to be able to do. Okay, and the way I do it is simply I say I take the time derivative of either r squared or r, you'll get to the same result. And I use the implicit chain rule to get me an expression in terms of the time derivatives of the previous coordinates. So if I take d dt of r squared, I get 2r times dr dt. And then I use the definition of r squared, and I simply write it out on this side, but that will be equals to 2x times dx dt plus 2y times dy dt. And so what I then get is that r dot is equals to x times x dot plus y times y dot over r. And what I then do, or will do later on, is I then go back and I replace what I know x dot to be and y dot to be with these expressions, and then I replace all the x's and y's with y, with the expressions in polar coordinates. So that's the basic approach. Okay, so let's do that now. So I'm going to have x times x dot. So here we have x times x dot over here, and y times y dot. And you can immediately see that this x squared plus y squared I can replace with an r squared, which makes things easier. You can also see what's going to happen. I'm going to have x minus y plus this xy term, so those are going to cancel. So in fact, I'm just going to be left with r squared times ax times x times, so it's ax squared, and an r squared times ay squared divided by r. And so the next step would be simply to write it as follows. So there I've cancelled out those two terms. Okay, I've replaced the x squared plus y squared with an r squared, and I've got another r squared coming on here to save me from all sorts of computational difficulties. And so I'm again going to have x squared here plus y squared over there divided by r, and I'm going to be able to write it like that, where I've now divided by r the r squared, and then finally I'm going to get this expression. So you can see this thing is a 1D equation. You can solve it analytically, and you can actually get an exact solution for the problem that you've had simply by choosing good coordinates. Okay, so we're not done because we have a two-dimensional system, and so we have to work out the time derivative of the other coordinate as well. And so we do that by working out theta dot. Okay, so I've taken this tan and I've written it as the written theta as the arctan of y over x, and so theta dot becomes basically d dt the arctan of y over x, and the arctan of y over x is simply 1 over 1 plus the argument squared, the whole thing squared, plus d dt of y over x. I then go on and I can multiply through by x squared, and I can basically, then I have an r squared below, and so then I have x squared times d dt of y over x. I use the quotient rule, and I'm left with this. Okay. So these steps, go through them again. They are useful, especially the polar coordinate system when you use it a lot. Practice it. So I now go back and do the same thing that I did previously. I replace the y dot and the x dot with the expressions that I was given to get the new differential equation. And so there I do it. Okay. And here you can see it's not going to be as a nice, cute cancellation as the past, but it's still going to simplify a lot. And so if I multiply out the brackets, I'm basically going to get that the term with a in front of it, so it's a times xy minus a times xy, that thing cancels out, and you're left with x squared plus y squared over r squared, and it's beautiful, it's equals to 1. Okay, so you can see that a differential equation that looked reasonably complicated over here in the new set of coordinates becomes actually something you can integrate directly. And so now let's see, now that we know we can find the exact answer for this differential equation, let's see whether what our prediction, what the center does, actually influences. Because look, we predicted from our linear analysis that the thing would be a center regardless of what the value A was. Okay, and that is not the full story. Okay, so the trajectory basically obeys those two equations, and let's now look what happens. Okay, so it decouples, and that's what I mean when the two equations separate out, is the decoupling of the equations in polar coordinates, and there we have it again. And so let's look at the implications of that. So the last equation is easy to solve. You simply have that theta minus its initial condition at times t0 is equals to time minus t0. Okay, so it's just a linearly increasing function with time. It's directly proportional to time. And so theta increases as a constant rate in time, and the R motion here, this one, is more complicated. It depends on the sign of A. So for example, if A is, let's just draw the drawing. So what we've got so far is, here's our xy space. A particular point is described by xy, where you have it r cos theta and r sine theta is the y, and we've just derived that our solution is going to be something that's described by the angle, and the angle is sort of going to move around with a constant motion in time. And so the R motion depends on the sign of A. So if A is less than 0, what we're going to have is that R dot is always less than 0 because R is a positive number. Okay, so if A is less than 0, the spiral is basically going to start somewhere. It's going to move around with constant velocity, and very, very slowly, or not so slowly depending on how big A is, its radius is going to decrease, and it's eventually going to be approached to 0. So you can see over here, even though the linearization predicts that you have a center, the nonlinear terms that A is the factor in front of is actually going to change what the solution looks like. Okay, so that's why I said if it's a borderline case, the prediction is not robust. If A is 0, then we made the right prediction. So only if A is 0 will the linear prediction match what truly happens. If A is greater than 0, you've basically got R dot equals to a positive constant, so R is going to increase, and regardless of how close you start near the origin, it's going to become unstable and spiral out to infinity. Okay, so the moral of the story is that for those borderline cases, whenever you're on those lines in the phase diagram, be careful, look at the full equation, possibly get a fancy coordinate transformation, or I'll tell you to explore a fancy coordinate transformation at this level. People have written theses guessing fancy coordinate transformations, so sometimes it's not easy. In fact, my thesis advisor was also a South African. That was actually when I studied at Cornell overseas, and my thesis advisor turned out to be a South African, and I didn't even know this. He became famous for, in the Einstein field equations, getting a really fancy coordinate transformation that allowed people to solve things analytically and basically opened up a field to a whole bunch of new analysis. So, yeah, so when these things, the coordinate transformations are hard to get, it's an art form. When you get good ones, you learn a lot about the system, so they're worthwhile looking for. Right, okay, so we've proven linearization is not the final word in analyzing a nonlinear system. What we're going to do now is start introducing other techniques of looking at these nonlinear systems that actually can give us answers in certain cases, even where linearization can't. And the first thing we're going to introduce, Okay, so that's basically the lesson that I've said. They're delicate. So the first thing we're going to introduce is another way of writing solutions in dynamical systems. And to do that, we're going to say, we're going to look at conserved quantities. And we're going to look in particular at, say, for example, the center, right? So if you get a dynamical system that is a center, it's a linear system, you can say, oh, the phase space is a center, and you know what it looks like. You can also say the phase space is a whole bunch of circles, and that describes it. But there's another way of making a whole bunch of circles. And if you were to think about a mountain like this, and you were to draw the contours on the mountain and collapse it onto a single surface, that would also be describing a whole bunch of circles. And so what conserved quantities does is it actually generalizes that idea, and it gives us another way of defining phase portraits that's distinct from the dynamical system. Okay, so let's look at what it is. So for example, now, a trajectory is a 1D curve in a two-dimensional phase space. Okay? One way of describing the curve is by means of an implicit equation. Okay, so the way we can describe that implicit equation is, say, f of x, y is equals to c. So think back of our mountain, right? Suppose we have z is equals to x squared plus y squared. That will give us a whole bunch of circles that looks like a cup. And suppose we choose a certain z value and then we cut through that mountain. Then we're going to make a circle with a certain z value. Okay, and at a different z value, we're going to have a different cut. So this is exactly what this equation says. One implicit equation in 2 dimensions will give you a curve. Okay, and if that curve is closed, you're going to have something like this, even distorted. You're going to have like a contour. And so conserved quantities is basically saying you have an expression like this that remains constant along the trajectory and can be used to describe the trajectory. Okay. So, for example, this is just the example, the mathematical example I've said. For the center, it's x squared plus y squared is equals to a constant. And we use this idea to characterize the solutions of ordinary differential equations. Not all of them, only some of them. But if we can find these functions, then we have a very good and powerful way of describing the solutions. And in fact, these conserved quantities play a crucial role if you start going up beyond 2 dimensions. In 2 dimensions, it's a beautiful way to illustrate it. It's a very nice way to do the calculations. But they become like gold when you go to higher dimensions. Okay. There's another famous guy in relativity, the Carter, Brandon Carter, that had a Carter constant named after him. He found the right variables to get those constants out, and he also made a whole bunch of calculations possible. So people get famous for getting conserved quantities in higher dimensions for important problems. Okay, so let's do it rigorously. So I'm going to define it for all dimensions. A conserved quantity is a quantity that, given a set of ODEs, so this is general, right? It's n-dimensional vector x dot equals to, say, n functions f of x. If you have that equation, and x is in Rn, then a conserved quantity e of x is simply defined as a real valued function such that e is constant along the trajectories. Okay, and the way we express that mathematically is, but there's a caveat, it can't just be a flat surface, it can't be identically constant. So that's the difference, right? The hump is changing, but for a certain circle, it is constant. So that's just to clarify that idea. So it can't be identically zero on an open set. And so the idea that it is constant along the trajectory, we write this way. It's basically ddt of E along x, where x is a parameterized vector of t that obeys this equation. Okay, so you basically have this, that ddt E of x is equals to 0 along the trajectories. And so using the chain rule, we can write it as follows, right? ddt is simply the gradient of E, in other words, the gradient of E with the derivative with respect to all the x's, dotted in with dx dt, which is basically that x dot, which is effectively f, must be 0. Okay, very powerful tool. If you can find these E's, you can say a lot about your trajectories. Okay, so here we basically have the definition of the conserved quantity. It is basically a quantity so that is not identically constant. In other words, the gradient doesn't vanish, and if you dot it in with x, it's 0. Okay. In 2 dimensions, it simplifies somewhat, right? It's easier to write down the components, and so let's do it. Let's look at the specific 2-dimensional case. So we have the ODE. We have x dot equals to f of x and y dot is equals to g of x and y, and x is an element of R2. And so our conserved quantity is now a function of x and y, and it's a conserved quantity if and only if its gradient is not 0, and the dEdt is equals to 0, and that is equivalent to saying that partial E with respect to x times x dot plus partial y with respect to y times y dot is equals to 0, which is also equivalent to saying as f of x and y times dE dx plus g of x and y times dy dx is equals to 0. So you can see here, this requires no time integration, right? So it's merely an algebraic calculation that you have to do to check if a thing is a conserved quantity, and it is very, very useful. Okay, so let's have a look at an example. So the first example is a mechanical system, which we get a lot in physics. It's a function that has this type of expression. The second derivative with respect to x times a constant is equals to f of x. And so where x is now just a scalar, or 1D function. And so we have 1 degree of freedom. And so when you work in mechanical systems, the degree of freedom is basically to the number of variables you have in the second order system. Note, it is not the order of the equation. Important. So a second order equation with 1 degree of freedom, you can basically write as a first order system with 2 variables. Okay, so this is a mechanical system. There's no damping in the system, and there's no driving. And so if we want to write this thing as a first order form, we're going to do the trick that we did very early on this course. We say x dot is equals to y. So we're introducing a new variable, and we're going to therefore have that x double dot is going to be y dot is going to be f of x over m. Okay, so now I want to say, so that's the differential equation. And it's true for any function of x. Now if you want to find a constant quantity, let us consider this quantity, basically, and I'll show you why we get it in a while. But for now, let's just illustrate what a constant is. E of x and y, that is equals to a half my squared plus v of x. Okay, so this v is a function we don't yet know. Let us look at it, and we know from our definition of a conserved quantity, it's a conserved quantity if and only if m, the derivative, the ddt of this thing is equals to 0. So if 0 is equals to e dot is equals to y dot plus the derivative of v with respect to x times x dot, if we substitute in the equations that we have for x and y, we get that E is a conserved quantity if and only if y times f of x plus y times v prime is equals to 0. And since we want this to be true for any y, it's equivalent to saying dv dx is equals to minus f of x. Okay. And so in 2 dimensions, there exists a conserved quantity such that E dot is equals to 0 along the trajectories, and we're done. And what's even more interesting over here, I've strategically named this F because it's in most cases it's a force. And so you can see that the conserved quantity over here is directly related to the integral of the force, which is a potential, and the kinetic energy. This term looks like a kinetic energy. So a conserved quantity is a mathematical concept that in physics often corresponds to the energy. And conservation of energy, conservation of angular momentum. So there's a very close connection. But strictly speaking, for the purposes of this course, stick to this definition in red, please. But you are welcome to use your intuition in guessing what form the conserved quantity is. Okay. So, in 2 dimensions, we're going to say that for a differential equations in 2 dimensions, if a conserved quantity exists such that E dot is 0 along the trajectories, that is what we're going to call a conservative system. Okay, it's just a definition. This is not true in 3 dimensions. In 3 dimensions, you need at least 2 of these functions in addition to the differential equations to get a conservative system. Right. Okay, so now we have another theorem. Now that we have the idea of a conservative system, we can introduce a number of theorems that are associated with systems for which we can get a conserved quantity. So the first theorem is a conservative system cannot have attracting fixed points. Okay, so, and an intuitive way of thinking about that is attracting fixed points will need you to get rid of energy, and for conservative systems, the energy is conserved. But to prove that, and so therefore it's not possible. To prove that rigorously, let's just do it. So for example, a stable node or a spiral are not possible for conservative systems. So there's systems that have a constant, a conserved quantity, they do not include all second order systems. Right? It's a subset of possible systems. But it's a very, very useful subset, as you'll see subsequently. Okay, so stable node or a spiral are not possible for a conservative system in 2 dimensions. And so let's just prove the theorem. So let's suppose we have a basin of attraction for a particular fixed point. It's going to be a proof by contradiction. Okay, so we have this basin of attraction. We have the fixed point and our trajectories go there. We know they can never cross by the fundamental theorem that's associated with the uniqueness and existence of ODEs. But fixed points are allowed. But now let's say we have this fixed point, we have the basin of attraction, so the region where trajectories have an initial condition that is going to end up at the fixed point. And if a conserved quantity exists, basically all points on the basin will have the same value, right? Because along a trajectory, the value of the conserved quantity doesn't change in time. So all the points on the basin are going to have the same value of E, whether it's here or whether it's there. And because they all share that fixed point, they're all going to have the same value. So basically, if E exists, its definition implies that it is constant over this finite area, which is a contradiction of what E is. Okay, so all points on the basin will have the same value of E. Basically, E of xy is equals to E at the fixed point. And since all trajectories approach the fixed point, and this contradicts the requirement, that E is not constant on a finite area or on an open set, and therefore the fixed point is not possible. Okay. So what is possible in a conservative system is basically it can't have any repelling fixed points as well for the same reason, because the trajectories are going to carry the value of the fixed point with them. So that's also not possible. So for a conservative system, you can only have saddles and centers. You can't have repelling things. Okay, so there's no such thing as a stable node, an unstable spiral. And so the conclusion of this theorem is that in conservative systems, fixed points are typically centers or saddles. Okay. And so that's one of the fundamental properties of our conservative system. And so let's look at an example, and I'm going to end with this example. In fact, I'm not going to do it completely, but I am going to do all the initial work for it. So let's consider a particle moving in a double well potential. So we basically have a potential that looks like this. So this is actually, I've plotted minus the potential over here. So we have a potential that looks like this. It's a double well potential. So the first order equation, or the second order equation, is simply x double dot is equals to minus dv dx. So it's basically moving up. The potential looks like that, so the force is the gradient of the potential. It's moving in this double well. And so that is equals to x minus x to the 3. Okay, we're going to write it in first order form. So we have x dot is equals to y, and y dot is equals to x minus the cubic of x. And so the analysis proceeds much as the song that I've been singing all along is you work out the fixed points, you work out the linearization, and then you begin plotting it. And you'll see that knowing that you have this this additional conserved quantity is actually going to help you in the end. But let's just do the preparatory work. You have fixed points. Fixed points occur when y is equals to 0 and when x times 1 minus x squared is equals to 0. So all our fixed points are on the x-axis, and they are at y equals to 0 and that equals to 0, which basically means that x can be 0 or plus minus 1. So that's where our 3 fixed points are. We can go on, we work out the Jacobian. It simply equals to this. So you already get a clue that you're going to be dealing with zero trace things. So you know you're in an indeterminate case. And so you can actually work it out at all the spots. So at the origin, it's basically the trace is just 0 and the determinant is minus 1, so you have a saddle. At plus minus 1, you have the same Jacobian, and you can work out the trace is 0 and the determinant is positive, so you have centers, okay, according to linearization. And it's a borderline case immediately because you have 0 eigenvalues entering in there. You're on the boundary. And so you need a further argument. And the further argument you can get to decide whether it's a nonlinear center is basically to see if you can get a conserved quantity. And from what we did in the previous case, all equations that obey this form, you can actually find the conserved quantity, and the conserved quantity looks like that, right? So you basically have the conserved quantity is just a half y squared plus minus 1 over 2 x squared plus 1 over 4 x to the 4th. And that tells you that along the trajectories, you have an expression like this. So it basically tells you that you have this hump thing, and the trajectories move along it, and the value remains constant. So even at the centers, you're going to have closed circles, so it's going to be a real center. And so it basically represents the kinetic energy plus the potential energy, and the trajectories are formed by curves of constant E equals to E of x and y equals to c. And these curves are closed around the linear centers, and therefore the centers are nonlinear centers. Okay, so you can see now that the conserved quantity that you can get in this way becomes very powerful, because it actually, not only is it going to give you the way of plotting the whole phase space, which I'll do in the next lecture quite slowly, because these are very important ways of getting solutions, but it also guarantees you that the linear analysis that would otherwise have given you a borderline case is actually giving you the real thing. Okay. And so I have 4 more minutes. Okay, so basically I have these nonlinear centers, okay. Before, what I'm going to do in the next 4 minutes, usually the rest of this course I always did it on talk and chalk, because it's really hard to make these pictures, but I have started actually making the pictures with a lot of coding, and so I can sort of give you the preview of the next lecture of how we're going to actually start using these conserved quantities to actually construct the phase diagram and what they actually mean. So I just actually want to get out of here. And I'll just make this, because I'm proud of my simulation, give you the preview. So I just want to give you what that conservative potential actually means and how we get the trajectories out. And then I'll give you sort of more, so this is just to get a feeling for it, and then next time I'm actually going to give you sort of concrete steps, more concrete than Strogatz does it actually, of how to use your conservative potential to actually draw the thing, because there are a number of tricks that he doesn't actually do that's very useful when sketching the thing. But firstly, let's just look at this conservative potential. Okay, so it's easy to prove that it doesn't change along the trajectories because we proved it in general, but also if you were simply to take the dot of all these things and substitute in the differential equation, you would be able to show that E dot is equals to 0. But let's now first try and draw this quantity, okay? So let's draw basically the quantity in the xy plane is down here below, and then you have E over here. And to draw it, the first thing is let's just pick a value. So let's pick y equals to 0. So if y equals to 0, the thing you're basically drawing is this quartic equation. So you work out where it crosses the x-axis, you work out where the derivative of this thing is 0, and you can factor it as well, so it's very easy to find out where it crosses the x-axis. And what you get is this line over here. Okay, so what happens now if you choose y to be a different value, okay, then it's simply going to be, once again, this equation equals to a constant, but a different constant. And so if you choose y a different value, you're simply going to get that it's that graph at 0 that's just moved up and down according to the y value. Okay, so y is going to introduce a constant. So that's if we keep y constant. We could do the same game and choose a specific x and plot what the graph looks like then, and it's just going to be a parabola with a varying intercept depending on what we x have. So we sort of made the ribs of our ship over here, and now we're going to pick an x, and we just have you can see the parabola sitting over here. So we have a whole bunch of parabolas that sort of fit into there. So you can see the quantity that we've actually plotted. We can see what this two-dimensional function of x and y is if we actually plot the whole thing. But we are interested, the part that we're going to use in what comes to describe our trajectories are simply the cases where exy equals to a constant. So if you want to plot those cases, you can imagine taking a sheet of paper, putting it in horizontally, and simply slicing this thing. And whenever you slice this thing, you're making the contours. And so let's do it. So the top slice, it looks like a peanut. And as your energy gets less, and then I'm going to draw its projection down onto the xy plane, because that's basically how we're going to go and construct what the phase diagram looks like. So then we can draw the peanut, we can go down, we can choose a different slice, and we know that slice doesn't change along the trajectory. So in our phase diagram, the slice is now down there, and we can keep going down over there until eventually we reach a point where you have this type of thing, where the hump in the middle is reached. That hump in the middle, you'll see next time. Somebody asked me in the beginning why it's called a saddle. Yeah. So that hump in the middle, that particular point there is the saddle point. And you can see, in some sense, if you were to put your legs down into the holes and the front would come like this, you would be sitting on a saddle. That's why it's called the saddle point, is because it's a direct connection to this conservative system. And I tried to explain it, and I did a really bad job the first time, but this is the sort of the cleaner explanation. So that thing, if we then, I haven't finished this yet, but if you then start drawing the trajectory, you're going to get something that actually looks like that projected down, and that's going to be your saddle point. If you go down lower, and I'll show you that next time, into these little humps, you're going to get little circles around the humps that are initially going to be squashed, and eventually they're going to be round, and those are going to be your centers. But we'll do that next time. Thank you very much for now. Thank you.